Here's part 4 of areas and distance. So notice as the width of the rectangles gets smaller, the upper and lower approximations become better approximations of the area under the curve. We need to increase the number of subintervals to as many as possible. This is why we look at the limit as the number of rectangles approach infinity. Your book proves that the limit as n approaches infinity of r sub n is equal to 1/3, which is the right-hand side method. Here, let's show that the limit as n approaches infinity of l sub n is equal to 1/3 as well. Before we take the limit, let's figure out what l sub n is equal to. So this means that we're taking our interval from 0 to 1 and breaking it up into n subintervals. So if I have my starting x value and being 0 and my ending x value being 1, if I'm breaking it into n subintervals, then my next x value would be 1 over n, and then my next x value would be 2 over n, and then 3 over n, and this would continue, and then my second to last one would be n minus 1 over n, and then 1 is the same thing as n over n. So that means that the width of each of my rectangles is 1 over n, and I want to figure out the heights of each of these. So the height of the first rectangle, since our function is x squared, it would be 0 squared. My next one would be 1 over n squared. My next one would be 2 over n squared. And this would continue on. Now, think about, because we're doing L sub n, our last height that we're going to use is dictated by n minus 1 over n, because again, we're using the left Riemann sum. So my last term in my sum would be n minus 1 over n quantity squared. We have L sub n is equal to 1 over n. My first term is 0, so I'll just get rid of that. And then my numerators for my remaining terms will be 1 squared, 2 squared, and my denominators would be n squared, since all of my denominators are n in the original fractions. And so all of these would be n squared. So what I'm going to do now is, since every single term has 1 over n squared, we can factor that out. What's going to be left over? Well, we'll have 1 squared plus 2 squared plus 3 squared, and then that will continue, and our last term will be n minus 1 quantity squared. We have L sub n is equal to 1 over n cubed times, let's take the thing inside of the brackets, so this long summation here, and let's rewrite that in sigma notation. We're going to be starting with I equals 1. What would our last term be, or last index? Our upper index is going to be n minus 1. And then the thing that we're summing is I squared. Now, you want to be a little bit careful here. Because we're doing a left-hand Riemann sum, the upper index is n minus 1. And the theorem that we learned about requires that our upper index be n and not n minus 1. So we have 1 over n cubed times, instead of plugging in n into the formula, we need to plug in n minus 1. So off to the side here, I'm just going to remind us that the theorem says if we have the summation from I equals 1 to n of I squared, that is equal to n times n plus 1 times 2n plus 1 over 6. So instead of plugging in n into this formula, we need to plug in n minus 1. Let's see if we can't clean that up a little bit. -1 plus 1, that gives us 0. And then we can distribute this 2. That would be 2n minus 2 plus 1, which would be 2n minus 1. So right now we have L sub n is equal to 1 over n cubed times n times n minus 1. And then the last term is going to simplify to 2n minus 1 over 6. And I'm going to go ahead and just simplify that so it's a single fraction. What you're going to notice is that if I expand out the numerator is going to be a cubic because our leading term would be n times n, and then n times n multiplying with 2n would be 2n cubed. So this is going to be equal to 2n cubed plus lower degree stuff. Why am I writing that? We'll see in just a second, over 6n cubed. The last thing that we need to do is we need to take the limit of L sub n as n approaches infinity. So if we do that, the limit as n approaches infinity of L sub n is equal to the limit as n approaches infinity of 2n cubed plus lower degree stuff, or plus lower degree terms, over 6n cubed. And since that's a rational function, we calculate that limit by looking at the ratio of the leading coefficients. So that's going to be 2 over 6, which is the same thing as 1/3. So we were trying to prove or show that that is equal to 1/3, which we've done. So I'm going to go ahead and conclude that proof. To create a general formula for area, let's consider a more general example. Let's say we have some function y equals f of x and it's continuous and non-negative. We will find capital A, the area under the curve y equals f of x to the x-axis on some interval from x equals a to x equals b. Let's divide the interval into n sub-intervals. What is the width of each rectangular strip or subinterval? Now be careful, the answer here is not 1 over n. Why is that? Well, in the previous example, we were looking between x equals 0 and x equals 1. So on our x-axis, if I look from 0 to 1, if I cut this up into n subintervals of equal width, then in that case, each rectangle would have a width of 1 over n. But here we're not starting at 0 and we're not ending at 1. We're using more general x values. So our first x value we're calling a, or x sub 0, and our last x value we're calling b, or x sub n. And what we're calling the width of each rectangular strip or subinterval, we call that delta x, which represents the change in the x values. And the way that we get it is we start with the endpoint and subtract off the starting point, which our endpoint is b and our starting point is a, and then we divide that by the number of subintervals that we're looking at. So does that work in the case that we were looking at in the previous example? It does, because b would have been 1, the a value would have been 0, and we would have divided that by n, so it would have been 1 over n, which was the width of each of those rectangles. But in general, the width of each rectangular strip or subinterval is given by the formula delta x equals b minus a over n. So now what we want to do is we want to figure out what are each of the individual x values. And so x sub 0 is just the a value, which is this same a value here. So x sub 0 is just equal to a. Now, I want to kind of a generic formula for the next x value, which I'm going to call x sub 1. And if I know that we're starting with the x value a, and I want to try to figure out what my next x value is, I know that the distance between here and here is delta x. So in order to get my next x value, which I'm calling x1, it's going to be a plus delta x. And that would give me my x1 value there. Well, how am I going to figure out my x2 value? Well, similarly, the distance between there and there is also delta x. So if I wanted x2, I can just take my x1 value and once again add on delta x. But there's a cleaner way to write that. So that is the same thing as a plus 2 delta x. Now I want a formula for x sub 3. Again, the distance between here and here is delta x, so I could take my previous x value, x sub 2, which was a plus 2 delta x, and then I can add on delta x, and a more condensed way of writing that is a plus 3 delta x. Are you starting to see the pattern? So if I wanted a general term, x sub I, let's say that was somewhere in the middle here, I don't know exactly where it is, the way that we would figure out x sub I is we would take our starting x value, which is a, and then we would add I times delta x. So notice that here our I value is 3, and that's why we have a 3 here. Here our I value is 2. That's why we have a 2 here. Here's a 1. Then the coefficient of the delta x there is 1. So this represents the general x value that we are looking at. So what I want now is I want a general formula for r sub n. I'm going to go ahead and erase these x values so I can have some space. I want a general formula for r sub n. It might be helpful if we start drawing a few of these rectangles. So my first rectangle, because these are right endpoint rectangles, I'm going to draw up from x sub 1 and then find the height there, and then that would be my first rectangle. My next rectangle would be there, and then that would be my next rectangle. X sub 4 would give me something like that, and that's going to continue on until my very last rectangle. And my very last rectangle, its height is dictated by the b value, or x sub n, and so that would stop and it would look something like that. So r sub n is going to equal the summation from, I'm starting with I equals 1 here and ending with x sub n. So we're going to have I equals 1 to n of each of my rectangles has a width of delta x, and then each of them has a height of f of x sub I, like that. So this represents the height of my rectangle, and then delta x represents my width of the rectangle. So that is the formula that we are looking for in terms of r sub n. Let's do a similar process very quickly to derive the formula for L sub n. So if I'm drawing my first rectangle, its height is going to be dictated by the very left endpoint, which in this case is x sub 0 or a. So that's going to be my first rectangle. And notice that was different than the first rectangle for r sub n. And then my next rectangle, its height would be dictated by x sub 1. So that's going to look something like that. And then x sub 2, it's going to look something like that. X sub 3 is going to look something like that. And so on and so forth. And then my last rectangle, here this would be x sub n minus 1. My last rectangle is going to have its height based on my second to last x value. So that's there. So L sub n is going to equal, it's going to look very similar to the formula that we have for R sub n. Can you think about what the only difference is? If you said the indices, you'd be correct. So my lower index would start at I equals 0 because the first height is dependent on x sub 0. And then it's going to stop at n minus 1 because that's affecting the height of my last rectangle. And the thing that we're summing is staying the same. So it'd be f of x sub I, which is the height, and then delta x, which is the width of our rectangle. So here are our formulas for R sub n and L sub n.